Welcome friends to EPG Pathshala and to the special module of ordinary differential equations part 3 in the paper of numerical methods under the subject of information technology. This is our third module in the series of ordinary differential equations. We began our journey with understanding of what a differential equation is, what is an ordinary differential equation, why do we need numerical methods to solve ordinary differential equations, and we classified the methods into two types, single step and multi-step methods, and we will also learn about the Taylor series method. So, in just 5 minutes, let us just take the recap of what we have learned in our previous two modules, so that we can have a continuation in our this module from where we left in the previous module. So, see what an initial first order initial value problem is. Dy by dx equal to f x y, and we are given the value of y at a point, initial point, which we call as x 0, which is given by y at the point x 0 is given as y 0. In the nature of numerical method says that we divide, if we have to need the value of y on the interval a b, we divide the interval a b into equal sub intervals x 0, x 1, x 2, x n with the uniform spacing h. So, x I is x 0 plus I h, and step by step we find the value of y at x 0, x 1, x 2, x 3, and then if you want to estimate the curve, we estimate the curve passing through those points, or if we need the values of y at the point b, we will step by step will reach b, because the step size has to be small. You have already learned in the second chapter, that is the truncation error, step size has to be made small. So, step by step from x 0 we go to x 1, x 2, x 3, and we reach the value of y at the point x n. So, the method is y at x 0 equal to y 0 is given, we get the value of y at x 1, that is given by y 1, from the value of y at the point x 0, that is y 0, and the function f. Then y 2 is determined using the value of y at the point x equal to x 2, and is estimated from the value of y at x 1, y 1, and maybe possibly y 0, depending upon whether we are using single step formula or multi step formula, and definitely we will need the value of estimate of the values of f, and this is how the process goes on. We begin with the single step methods. See, we classify the method into two types, one which are called single step methods and other which are called multi step methods. See, single step methods use the value of y at only one previous step, like y 2 will use the value of y at x 1, and the previous values will not be used. Y 3, if we want, that is y at the point x equal to x 3, it will use the value of y at the point x equal to x 2 and function values, but it will not use the value of at further previous steps. So, these are single step formulas. We are right now learning single step formulas, and then in the later section of today's module, we will go to what are called as multi step methods, which use the value of y at more than one previous step. So, the nature of the single step methods are, they are single step as they are direct methods, and because they are direct, they are not iterative. They are, all of these formulas are based on the Taylor series method, they emulate Taylor series, all the single step methods, and they use the value of only at one previous step and the function information, and because they are single step formulas and because they are direct formulas, the error estimate cannot be made in their cases, because we do not know what the actual error term value is. Definitely we have theoretically idea about order of h. So, error term is order of h cube, h raised to 4, depending upon what order formula we are using, but we do not know, because we do not know the value of derivative of the function at the point xi, xi is not known to us, and that is how we cannot estimate actual error. So, the Taylor series method is the backbone, and it is a theoretical method. We can use it to derive a formula of any order, but it lacks practical implementation for the simple reason that we need to evaluate the value of derivative of function at the points, and if the function f x y is not convenient, the derivative calculations manual one has to do, and then one has to implement in the program. So, the program will change from problem to problem, and that is why, and it needs the evaluation of derivatives. So, it is not convenient to implement for computations practically. And based on this, there are other formulas which are derived. The n equal to 1 case we get Euler formula, and n equal to 2 onwards there is a family of formulas which are called Runge formulas. So, in the case of Taylor series method, see this is the Taylor series, and if you look at the second bullet, that is up to nth term if we retain, we need the derivative of y up to at the point x equal to x I we need to calculate, and if we ignore the last term n plus 1th term, then this Taylor series formula used for approximating value of y at x equal to x I plus 1 would be the Taylor series formula of order n. So, based on this Taylor series method, we have the family of Runge formulas. Now, these Runge formulas are the family, means they can derive of any order, and all of them are single step methods. They are you can get them of any order like order 2, order 3, order 4 and so on. And see, they all are named after the two mathematicians Runge and Kutta, and they all are based on the Taylor series. And the advantage of these formulas is analytic differentiation is not required, you need only the function evaluation. So, let us come to Runge method of order 2. It is equivalent to Taylor series method of order 2. It is derived by retaining terms up to second power of h and ignoring higher order terms. So, local error is of the order of h cube, and the advantage is that it requires only 2 function evaluations per step, and because of only there is no need of differentiation. So, this Runge formula of order 2 looks like this is the formula k 0 is h f x y I, and this is how we method which is used, which we had seen last time, that is the both side Taylor series. You try to derive the formula of the type y I plus 1 is y I plus a k 0 plus b k 1. K 0 is given by h f x I y I and k 1 is given by h f x I plus alpha h y I plus beta k 0. Taylor series of 2 variable is used and it is expanded, and here you substitute these values, equations are formed, number of equations are less than the number of unknowns. So, more than one solution are there, and so the one convenient solution here is given by the formula y I plus 1 is y I plus half k 0 plus k 1, k 0 is h f x I y, k 1 is h f x I plus h y I plus k 0. So, this is the Runge formula of order 2. We had solved one example also. Your illustration we used dy by dx is x minus y, y at 0 is minus 2 and x 0 becomes 0, y 0 becomes minus 2, and we use this formula to calculate k 0, k 1, and we got the value of y 1 as minus 1.62. Now, once you get y 1, then we can again substitute in this formula, y 1 is there, I will become 1 now. So, like I was 0, we got y 1 is y 0 plus half k 0 plus k 1. I will become next time I will become 1. So, y 2 will be y 1 plus half k 0 plus k 1. Now, new k 0 k 1 will have to be calculated, k 0 will become h f, instead of x 0 y 0 it will become h f x 1 y 1, and k 1 will become h f x 1 plus h y 1 plus k 0, and this is how we will get y at x 2, and this will go on. So, the program was designed, and when implemented, this is how for this particular example the computation table looks like. If the function is x minus y, x 0 is 0, this is the of course x 0 minus 2, h step size is chosen as 0.2, approximation solution is minus 1.62. Now, this is used to calculate at x equal to x 2 y 2. So, at x equal to 0.4 x 2, that is y 2 comes out to be minus 1.2724. Now, this would be used, and again new k 0 k 1 will be calculated. So, x 3 becomes x 2 plus h 0.4 plus 0.2 and y 2 is minus 1.272. New value of k 0 and k 1 are calculated, and this is how the series of approximate solution is generated. At 1, the value of y comes out to be minus 0.370740, that is, and exact solution is minus 0.367879, giving us absolute error of 0.002860 and percentage relative error at 0.77, less than 1% it is. Now, if you reduce the step size, let us say h equal to 0.1, half of what it was. So, to reach 1 now we need 10 steps, and same process, same formula is applied again. So, we get the value at 1 now minus 0.368541, and so the absolute error has reduced to now 0.000662. So, up to 3 decimal places the answer is correct, and the percent relative error has come down to be 0.179826. See, if you look at the previous slide, see this percent relative error, as we further go, this is increasing, this, and here also the absolute error is increasing for the simple reason. The reason is y1, when you are calculating from y0, this is erroneous, this is not exact. Now, this is used to calculate y2, y3 is calculated using y2. So, this error goes on cumulative, it goes on accumulating. As a result, as we go ahead the points, the error goes on increasing because of not only truncation error, because of error, inherent error like y4, then you are using y3, y3 contains the error, because y3 contains the error, because y2 contains the error, and so on. So, this error goes on propagating. Further, if you reduce h equal to 0.05, then if you look at the results, final result, then the error is, the approximate value is minus 0.368039, exact solution is minus 0.36879, and percent relative error is 0.043270. So, let us compare these results, and if we compare these results, what we find is, see, if we look at the step sizes 0.2, 0.1, 0.05, the error at 0.2 is 0.002860, at 0.1 0.00662, at 0.05 0.000159, and so percent error is, here is almost 1%, 0.178% and 0.0432%. So, this confirms us with the fact that as we reduce the step size, the reduction of step size introduces the more accuracy, results are more accurate, because the error is of the order of h cube in the Runge-Kutta formula of order 2. We have taken up to the terms of order of h square. So, as we reduce the step size, the truncation error will go on decreasing. Of course, there would be limit of reducing the step size, because then round off error will start playing more role, and also the error propagation will start playing the more role. So, beyond a particular limit, the reduction of the step size will not yield the result, but definitely as we reduce the step size, truncation error decreases. So, our estimate for the result, it improves, the accuracy is improved. Let us take the second illustration, dy by dx is x upon y, y0 is 1, and again we repeat the same process. So, our table is here, manually we have calculated y1 is y0 plus half, k0 plus k1, h is 0.5, we are taking the step size, and fxy is x upon y in this case. So, k0 is h, f01, 0 upon 1 is 0. So, this gives 0, k1 is point h, f x0 plus h, y0 plus k0, x0 is 0, y0 being 1, and so 0 plus 0.5, y0 is 1, 1 plus k0, so 0. So, h f x0 plus h, y0 plus k0. So, k1 become 0.5, f of 0.5 by 1, 0.5 comma 1, f x y is x by y. So, 0.5 into 0.5 by 1, result is 0.25, and so y1 will be calculated as y0 plus half, k0 plus k1, giving us y0 is 1 plus half, 0 plus 0.25, result is 1.125. Now, again you repeat the process. So, y2 will become y1 plus half, k0 plus k1, and k0 is h f x1 y1, h is again 0.5, x1 now is x0 plus h 0.5, and y1 is 1.125. Repeat this and similarly repeat it. So, we get y2 as 1.42167812. So, this is how we have to proceed, and again the program, if we can use it or you do it manually. So, h equal to 1. So, only 5 steps to reach 5. We get approximate solution as 5.125. So, step size is quite large, as equal to 1, still the answer is correct up to 1 decimal place. The absolute error is 0.026227, and percent relative error is 0.514335. And if you reduce the step size from 1 to 0.5, then approximate solution is 5.101263. So, error is 0.0022. See, it has become correct to 2 decimal places, and the percent relative error has boiled down to 0.044005. And further one more step, h equal to 0.25, then it is C 0.099266, 0.099020. So, up to 3 decimal places we have got the answer correct, 0.000246, and percent relative error is 0.004833. So, this is the comparative chart again, h equal to 1 less than half percent relative error, 0.5 less than 0.04% and 0.25 less than 0.004%. Result correct up to 3 decimal places, here up to 2 decimal places, at 1 it was result up to 1 decimal place. So, in this example, reduction of step size by 1 is increasing the accuracy for up to 1 more decimal place in this example. It all depends upon the function and other things. Now, with this let us come to example of Runge-Kutta method of order 4. So, as I said, Runge-Kutta is a family of formulas for any n, means n equal to 2, n equal to 3, n equal to 4 and onwards we can derive Runge-Kutta formula of any order. No doubt the derivation becomes very laborious and complex as our n becomes high, but somehow Runge-Kutta formula of order 3, it is available in the literature, those who are interested can refer it, but is not much very popular in practice, and directly we are going to Runge-Kutta formula of order 4. Now, as the name is order 4, it is based on the Taylor series of order 4, means the terms up to h raised to 4 will be retained and terms of h raised to 5 onwards are ignored in this Runge-Kutta formula of order 4. So, it is equivalent to Taylor series of order 4, and again in this formula there are four formulas k 0, k 1, k 2 and k 3. So, 4 function evaluations would be required in each step, and there is no differentiation procedure. Local order error is of the order of h raised to 5. This is the formula for Runge-Kutta formula of order 4. This is our initial value problem. yi plus 1 is yi plus 1 by 6. There are 4 terms k 0, k 1, k 2 and k 3. K 0 is as h f x I yi, the same which we had in the order 2. K 1 is now h f x I plus h by 2, and yi plus this k 0 is calculated yi plus k 0 by 2. Now, we know k 0 and k 1, k 2 is determined by h f x I plus h by 2, yi plus k 1 by 2, and k 2 is known, k 3 is h f x I plus h and yi plus k 2. So, we need 4 function evaluations, f x I yi, f x I plus h by 2, yi plus k 0 by 2, h f x I plus h by 2, yi plus k 1 by 2 and f x I plus h yi plus k 2. So, these are k 0, k 1, k 2, k 3 and the weighted average of them k 0 plus 2 k 1 plus 2 k 2 plus k 3. Sum of the coefficients is 6 here. So, this divided by 6, this is added to yi to get the estimate of y at the point x I plus 1, that is yi plus 1. Again, let us take the same example and compare the results. So, step size h is equal to 0.2, but now you can realize, see that at 1 the same h equal to 0.2 we are taking, approximate solution is minus 0.367883 and very near to exact solution, it is almost 5 decimal places, the answer is correct, and we have retained the figures up to only 6 decimal place. So, they are being rounded up to 6 decimal place. So, here the round off error will also play the role. So, percent relative error is 0.000975. Basically, this is almost, I mean the result is correct up to 6 decimal places, and so h equal to 0.1 further, I mean it has further reduced, almost it has become 2 here in the last decimal place and the error has reduced. So, this is the table, there was no point in reducing h further. So, only 2 steps 0.2 and 0.1 we have taken, and practically we can say that there is almost no error up to 6 decimal places, the estimate is correct up to 6 decimal places. So, order h raised to 4 is much more stable and gives quite good results as compared to Runge-Kutta method of order 2. So, this is the chart you compare, we have 4 methods it compares. The Runge-Kutta method 2 is green color and Taylor order 2 is this red color, and RK4 and Taylor order 4. So, you can very well say if the H is 0.2, see here this is the percent relative error and this is 0.1, 0.2, it is going only up to 1%. So, do not feel that the error is so large, it is only 1%. So, in case of H equal to 0.2, it is a 0.77, and in case of x minus y, the results of RK2 and Taylor series order 2 function is linear, and as a result Taylor series order 2 and RK2 both are giving the same estimates. So, error is also same. So, RK2 and Taylor order 2, the result is error is 0.1%, for others it is practically nil, and for H equal to 0.1 it is 0.18% in case of RK2 and Taylor order 2, and order 4, Taylor order 4 and RK order 4 are giving almost practically nil error, and for H equal to 0.05 all the methods are practically giving us no error. So, step size 0.05, all the methods are giving no error. For 0.1, RK2 and Taylor order 2 are giving 0.17% error, and others are giving practically no error, and H equal to 0.2, RK4 and Taylor order 4 are giving no error, whereas these two are giving about 0.1%, this is about 0.8% relative error. So, this is the same thing, the chart. The only thing is I have included Euler method also here in this chart. Say H equal to 0.2, Euler is 10.9, almost 11% error, and Taylor order 2 0.77% error, and of course, these are already you have seen in the graph. So, but if you look row wise, 0.2 Euler 11%, Taylor order 2 0.77, RK 2 0.77, these are percent relative error, and Taylor order 4 0.001% and RK 4 still less 0.0009%. So, almost practically nil error, and H equal to 0.1 Euler error has come down to 5%, and Taylor order 2 error has come down to 0.18%, RK2 also same, and Taylor order 4 practically they have no error, and 0.05 Euler is 2.55, Taylor order 2.04%, RK2 also same, and order 4 and them they have no practical error. Now, let us come to second illustration, x by y, the same exercise if we repeat for this. Here H equal to 1, this is the absolute error 0.001477, percent relative error is 0.028, and further reduce the step size almost up to 4 decimal place, the answer is correct, and if you further reduce, answer is almost correct up to, it is correct up to 5 decimal place, almost correct up to 6 decimal place. So, if we compare the in case of RK4 result using different step sizes reduction, then error is reducing from 001 to 0.000008. So, changing the step size to half is introducing the accuracy at up to 2 decimal places is increasing. It depends upon the nature of the function, it is x by y, and so percent relative error is coming down from 0.03% to 0.0001%, a very accurate result. So, this is how the chart looks in this case. Because it is function is not linear, the Taylor order 2 and RK2 you are finding the difference. Taylor order 2 error is much more compared to RK2. So, RK2 is convenient to use, at the same time error is also less. Of course, RK4 is giving practically no error in all the cases, 1.5 and 0.25 step size, and this RK2 also for step size 0.5 and 0.25 practically no error, only Taylor order 2 is, here it is 1.37% and here it has come down to 0.27%. So, RK2 is very good and RK4 and R is very used. Taylor order formulas are practically not suitable. So, this is a comparison. Here Euler formula also we have included in the table, and in case of Euler formula inclusion, you can look H equal to 1, 1.94% relative error, Taylor order 2 1.33, RK2 still 0.51%. We have not used Taylor order 4 for x by y, because fourth order derivative of this function, the expressions become quite laborious, complex and to implement. So, and we have not bothered to implement it, and RK4 is 0.028, 0.029%. So, 0.5, see Euler has come down to 1.23, Taylor order 2.27, RK2 0.044 and RK4 to 0.001%. So, this is how, see, Euler is reducing with the step size, but some error is there. Taylor order 2 is performing much better compared to Euler, and RK2 is performing much better compared to Taylor order. So, they are of the same order. Taylor order 2 is expected to perform much better than the Euler, because Euler is Taylor of order 1, but RK2 is performing better than Taylor order 2 and convenient to apply, and RK4 is of course 4th order. So, definitely expected to perform better than this formula. So, with this our single step formula, same way the one can have the Runge-Kutta formulas of order more than 4 also. So, with this now let us move to multi-step formulas. See, what is the nature of multi-step formulas? First thing is that as the name is multi-step, they use the value of y at more than one previous step. You can have 2-step multi-step formula, 3-step multi-step formulas, 4 steps, so on. The most common being 4-step, as in the case of Runge-Kutta order 4 is most common. Similarly, here also in the case of multi-step formulas of order 4 are the most common methods to be used. They have one very great disadvantage, and that is that they are not self-starting, because you need the value of, if I am using the multi-step formula with the 4 previous steps, I need the estimate of the value of y at 4 previous steps. So, one may have to use either Runge-Kutta formula or any other formula to get the estimates at the 4 previous steps, and then only one can begin. And quite good formula should have been used, because otherwise those 4 previous step results will contain the errors, and those errors will propagate when we apply multi-step formulas. And of course, in the case of multi-step formula also, if you are using 4-step, error is of the order of h raised to 5. If you are using 2-step multi-step formula, error is of the order of h cube, and so on. And but they are supposed to be less stable. Of course, no common sweeping statement can be made about them, but they have been found to be unstable for certain examples, whereas Runge-Kutta formulas have been found to be more stable for the examples. So, these are the disadvantages. They are not self-starting, and they are most commonly 2-step and 4-step methods. The one great advantage there is that, like if you are using 4-step formulas, they are computationally faster. Their derivation is based on the numerical integration of interpolating polynomial fitted at the previous steps, and preferably the backward difference interpolating polynomial is used. The most common multi-step formula known as Adams-Bashforth method. See, in these 4-step formulas, the coefficient term is usually larger than that in Runge-Kutta formulas, and so generally the Runge-Kutta formulas are more accurate than these corresponding multi-step formulas. The advantage of these 2 multi-step formulas is that the function evaluation, only one function evaluation per step is required, whereas in the case of Runge-Kutta family of order 4, 4 function evaluations are required. So, they become computationally faster, less expensive to use, but of course, memory wise they are more expensive, because they need to store the values of 4 previous steps, and computationally wise also, programming wise also, they are little more laborious, little more difficult to implement as compared to Runge-Kutta formulas, because they are simply direct formula implementation, but here you need to look and store the previous values. Now, in this case of multi-step formulas, we can classify them into 2 types. One is the open type, which we call as explicit formulas, and the other which we call as closed type, which are implicit formulas. Let us learn the nature of these open type explicit formulas first. See, the equation is dy by dx is f x y x, y x 0 is y 0, and let us denote, see, f at the point x I, y at the point x I we call y I, this much we know, and this function value of f at the point x I y I is derivative of y at the point x equal to x I. So, this is y I dash, let us call it, and we will denote this for simplicity purpose f I. So, what is f I? Our notation is f at the point x I y I. What is x I? x 0 plus I h, where h is the step size, and y I is the value of y at the point x equal to x I. So, the most common, the most popular Adams-Bashforth 4-step explicit formula is yi plus 1 is given by yi plus h by 24, 55 fi means 55 f at the point xi yi minus 59 f I minus 1 means f at the point xi minus 1 yi minus 1 plus 37 f at the point xi minus 2 yi minus 2 minus 9 f at the point xi minus 3 yi minus 3. So, this is the most common Adams-Bashforth formula. Error would be the order of h raised to 5. See, if we need the value at the x point xi plus 1, we need the value of y at 4 previous steps I minus 3, I minus 2, I minus 1, I. So, you can start I equal to 3 only, you need the value at x0, x1, x2 and x3, and then we can estimate the value of y at x4, that is y4. There are other lower order formulas also like yi plus 1, here is yi minus 3 plus 4 h by 3, 2 fi minus fi minus 1 plus 2 fi minus 2. So, this is our uses the value at 3 previous steps, and similarly this is the one which uses only 2 previous steps. So, you can have 2-step formula, 3-step formula, 4-step formula. 4-step formula is the most common to be used. As we have open type formulas, see in the case of open type formulas, we are approximating function by interpolating polynomial, usually backward difference polynomial is used for derivation at 4 previous points. Now, similarly, involving xi plus 1 also, the interpolating polynomial is used, and that numerical polynomial is integrated using numerical integration to get the estimate of y at the point xi plus 1, and the formula so called are called closed type, because you are using the point x equal to xi plus 1 also in derivation of the formula, and they are also called implicit formula. Why are they called implicit formula? I will explain you just now. So, we get what are known as closed type multi-step formulas. So, let us look at this closed type multi-step formulas. See, the simplest example is yi plus 1, it is only 2 step I am illustrating you, yi plus h by 2, fi plus fi plus 1. So, here see you are using the point xi plus 1, yi plus 1 also. So, this is the formula. So, fi plus 1 is yi plus 1 dash is the fx plus 1 yi plus 1. To illustrate you, if I take the same example, dy by dx is x minus y. So, fx y will be x minus y. So, yi plus 1 becomes yi plus h by 2, fi plus fi plus 1, fi is xi minus yi, fi plus 1 will become xi plus 1 minus yi plus 1. So, it is called closed type, it is very obvious because we are using xi plus 1 in the formula. Now, why is it been called implicit is because the right side also contains the value of yi plus 1 which is unknown. So, you have to take the terms all containing yi plus 1 together and then you have to solve it. So, directly you do not get the values, it is yi plus 1 is included implicitly in the equation. And so, here if I have to take the yi plus 1 term on the left side and then form the equation, express yi plus 1 and then solve it. So, the difficulty in these implicit formulas is here it was very easy because x minus y is linear, but the cases where f x y is not a simple function, then here this fi plus 1 will need not be linear, and then it will involve the equation will be formed which is a non-linear equation to be solved to get the coefficient of yi plus 1, and that makes the process laborious. As a result, we have a special case of multi-step formulas which are called predictor corrector formulas. So, we get it is a hybrid of explicit and implicit formulas. The first, see the explicit formula is used as a predictor, like Adams-Bashforth may be used and other may be used, and then after using the Adams-Bashforth formula, see it is has two formulas. Explicit is called predictor, one time applied to predict the value, and implicit is called corrector. So, we use two formulas, explicit is predictor and the one which has implicit we call it corrector, and it is iteratively applied till two successive values lie nearby within the tolerable limits. and if the step size is properly chosen, then one need not have to go beyond 1 or 2 iterations, the value stabilizes and you get the answer correct to number of decimal places. If it does not stabilize in after 2 iterations, that means one has to work again, reduce the step size and has to work further. The step size chosen is not a proper step size, because the corrector formula is more accurate than the predictor formula, and definitely it needs to and stabilizes, the estimate stabilizes after 1 iteration normally or at most 2 iterations. So, if more than it is not stabilizing, that means the H step size has to be reduced and it has to be reworked again. So, let us take the example, I mean the formula. So, like 4 step Adams Bashforth, this is the one which you have learned, the formula which is the multi-step explicit formula. This will be used as predictor and corrector is y I plus 1. This is just shown for your understanding. Y I plus 1 at the kth step, because it is iterative, is y I plus h by 24. 9, this is nothing but f I plus 1 plus 19 f I minus 5 f I minus 1 plus 37 f I minus 2. So, the working will be, we have these 4 values, they would be used to get y I plus 1. Once we get y I plus 1, f I minus 1, f I minus 2 is available. This is f I plus 1. So, this y I plus 1, I may call it 0, 0th iteration predictor, will be substituted here like k equal to 1 here, first step. And so, you have y I plus 1 from predictor formula. This will be substituted to get the value of y I plus 1 corrector formula. This is Adams-Moulton formula. Now, once this y I plus 1 is obtained, again this will second iteration, this is first iteration, it will become input here. So, f x for with this new y I plus 1, f x I plus 1, y I plus 1 will be calculated, and again you get y I plus 1. This new y I plus 1 will be compared with the older y I plus 1. If this absolute value of this difference is less than epsilon tolerance limit, the same method of process of iterative method, then we will stop. If it is not less than tolerance limit, we will again step further, we will find y I plus 1 2, and y I plus 1 2 will be y I plus h by 24, 9 f x I plus 1, y I plus 1 1 plus the same values, and new value again compare it. Still if the value is not less than epsilon, that means the one needs to reduce the step size, maybe make it half, again work it and again work these iterative methods. So, the advantage of this is that because we are calculating y I plus 1 minus y I and we are ensuring it is less than epsilon, we have the estimate that how accurate the result is. Now, similarly, the more convenient is the Milne predictor formula. Y I plus 1 is y I minus 3 plus 4 h by 3 2 f I minus f I minus 1 plus 2 f I minus 2. This is predictor, and corrector is nothing but the Simpson's 1/3 formula which we have learned in the numerical integration. Y I plus 1 is y I minus 1 plus h by 3 f I plus 1 plus 4 f I plus f I minus 1, and same technique is used. This corrector formula will be iterative, you will apply it again to and again till you get the desired accuracy, but again the same principle that more than 2 implementations of corrector formula is not desired, that will mean to reduce the step size. So, if you look at these predictor corrector formulas, they have 2 great advantages. The one great advantage is less number of computations, only one function evaluation per step, because all other values are available. And the second advantage is we get the desired accuracy estimate. Disadvantage of them is they are not self starting, they require more memory in the computer. Though they are fast, less computationally expensive, but if we have to play with the step size, the implementation becomes quite laborious. Programming wise, predictor formula, then the corrector has to be iterative. If you do not get the desired accuracy, you have to come out, reduce the step size. So, programming implementation is more cumbersome, more laborious as compared to Runge-Kutta family of formulas, and many times these methods are not that stable also. stability can become an issue in the case of predictor corrector formulas. But in a nutshell, the Runkuta formulas and the predictor formulas, both they are the two most common formulas to use in the solving differential equation. Earlier Runkuta formulas were had the very high priority, but now even predictor corrector formulas are being used to solve it. So, this is the comparison chart, if you can have a look at them. Runkuta formulas, the advantage is they are self starting, they are stable, you get good accuracy in them, as you have seen in the earlier examples also. The only thing is, but you cannot guarantee that okay, the answer is this much accurate, because we have no idea about, only we have the idea of order of h raised to 5 h cube depending upon what formula we are using, but actually how much, because there are other terms involved, we cannot, actual error we cannot tell. In the case of predictor corrector methods, Runkuta are self starting, they are not self starting. They may be numerically unstable, but since you are using corrector formula iteratively, you know okay, the answer is correct to these many decimal places. Runkuta formula being direct and only single step formulas, they require less memory, whereas here they require more memory and program writing is not that easy. And here in the case of Runkuta formula, because you are direct, all you have is h raised to 5. So, there is no such systematic method of knowing what should be the proper step size for a particular example, but here because of the being iterative in nature, you can go on reducing the step size till you get the desired accuracy. So, automatically exact proper step size you arrive at. And Runkuta method, the one more disadvantage is 4 function evaluations per step are needed, whereas in the case of predictor corrector formulas, the only 2 function evaluations, one for predictor and one in the case of corrector are being used in the per step. So, this is about the predictor corrector formulas and the methods to solve ordinary differential equations. The results and the computational results and the manual computations of are illustrated using predictor corrector formulas in the e-text. So, those who are interested, you can refer e-text, there the results are displayed. And with this we complete the chapter on the ordinary differential equations. Those who are interested in learning more about these methods and want to learn other methods also, you can please refer to the additional reading references. Good books are listed there and you would be able to learn more about them. And so, with this we will move to next module. Bye till then, wish you happy learning.